Hi everybody. This is Unit 3 and it's on ordinary general annuities. So what you're going to notice is this is very similar to Unit 2, but there's one difference, and you'll see this topic is ordinary general annuities. Unit 2 focused on ordinary simple annuities. Okay, so just as a recap, remember from Unit 2, okay, that annuities are a series of equal payments. Okay, and they're made at certain intervals, monthly, quarterly, weekly even. And the length of time between your payments, between when you make a payment and when you make your next payment, is the payment interval or payment period. And the total length of time for the annuity is called the term. Okay, so let's say your annuity is 5 years in length. The amount of each payment is known as the periodic payment. So remember, our Unit 2 talked about ordinary simple annuities. So in this instance, the compounding frequency and the payment period are the same. Remember, the compounding frequency is how often you're earning interest. So if interest was earned quarterly, you made your payments quarterly. That was an ordinary simple annuity. An ordinary general annuity, which is Unit 3, is where the compounding frequency and payment period are not the same. This is very common in applications such as a mortgage, where you might have bi-weekly payments or monthly payments, but your interest is only compounded twice a year or semi-annually. Okay, so there's one small change that we have to make to our equations that we learned from last unit in order to apply them to an ordinary general annuity. So let's just look at kind of what this means when there's a difference. So like I said, the compounding periods for interest and the payment periods are not the same. Okay, so let's look at an example. If we had $100 that we deposited every 6 months, okay, so every 6 months means semi-annually, for 3 years, with interest at 4% per annum compounded annually. Okay, so if we're looking at the future value, there's two things to consider here. Okay, our payment periods, each of them are 6 months apart. So every 6 months, we're depositing $100. But every year, right, because it's annually, we're earning interest. Okay, so when we're looking at it, we need to have one common value. Okay, that takes into account the number of times you're paying still, but also what your interest rate ends up being, right? So we need to find an equivalent interest rate that actually applies, in this case, for semi-annually. All right? So how we do that is we actually look at the ratio. What is the ratio of the number of interest compounding periods and the number of payment periods? Okay, and we call that ratio C. It doesn't actually mean any specific item, it's just the letter C. So like I said, that's a ratio. Remember, that's from our third unit from the previous course. So for the last example, for instance, our value of C, the number of interest compounding periods, remember it was annually for the question we looked at. So that means 1. And the number of payments, remember we made payments every 6 months, which was semi-annually. So the value in the denominator is 2. So your ratio is 1/2, right? So that number becomes important, all right, because there's an equation that was developed to find an equivalent interest rate that you can use instead of the periodic interest rate I in each one of your formulas, all right? So that ratio is actually used to find an equivalent interest rate. So remember, in that first example, we had $100 and you paid that semi-annually. But your interest was compounded annually. So to make up for that difference, right, in that your interest is compounded less often than your payments, this formula finds an equivalent rate of interest per payment period. So for each payment period in this style of question. And what it is simply is it's that same term we've seen a lot, 1 plus the interest rate, I. Remember, that's the same thing, the periodic interest rate. And it's the same, it's equal to J divided by M. Okay? So it's 1 plus I, and all of that is raised to the exponent C. And C is that ratio we talked about, the number of interest compounding periods divided by the number of payment periods per year. And then this minus 1 actually allows you to come up with an interest rate, because you have to subtract 1 from this number. So this formula is going to become very important. Okay? Let's see how we use it. So once you know that formula, if you remember, I'm going to look at future value now. The only change is that everywhere in your future value formula where I was located, you replace it with P. So what I've noted this is future value, and I've noted a subscript G. That just means general annuity. That's just so I can note the difference between it from a general annuity to our last unit, which was a simple annuity. So the formula didn't change. It's payment times, and then in brackets, 1 plus, and instead of I replaced it with P, the exponent n minus 1 divided by P. N is still the total number of periodic payments, or total number of payment periods. P is now that equivalent rate of interest, which is that formula that I showed you on the last slide. The payment is still the same. PMT is still the periodic payment. And future value, FV, is the same, except in this instance, the future value you calculate is for an ordinary general annuity. So there's no difference. The formula in your second unit was future value is equal to payment times 1 plus I to the exponent n minus 1 over I. All what I've done is replaced the i's with this new term, P. Okay? So let's look at an example where we use this. Determine the accumulated value after 10 years if you pay $2,000 at the end of each year if interest is 6% per annum compounded monthly. All right, so one thing you notice here, you're paying $2,000 at the end of each year, that's annually, and your interest, 6%, is compounded monthly. So the compounding frequency and the payment period frequency are not the same. So this is an ordinary general annuity. That's how you can tell. Okay. One other item that is the same as a simple annuity is payments are made at the end of each payment period. That makes it an ordinary annuity. So now that we know that, okay, and we're trying to find the accumulated value, we're trying to find the future value. So again, I'm putting this subscript G. That just means that it's for a ordinary general annuity. So that's equal to your payment times 1 plus, remember this term P, to the exponent n minus 1 divided by, whoops, not I, P. See, all we're doing is replacing I, P. So there's a couple terms that we need to find here. Okay, first, our payment. In this case, we know it's $2,000. It's given in the question. And now we do the same steps that we've done before. All right, we know that our nominal interest rate, J, is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. M, okay, our number of compounding periods per year is 12. So we can calculate our periodic interest rate, I, which is equal to J divided by M. That's equal to 0.06 divided by 12, or 0.005. The only difference, okay, is we need to use this to calculate this interest rate P. Okay, so before we do that, we have to calculate the ratio C. Remember, that's the number of interest periods divided by the number of payment periods. Oops, that's bad handwriting, periods. Okay, so interest is compounded monthly, so that value is 12, and your payments are yearly. So it's 12 divided by 1, which gives you 12. So now, okay, we've added 2 steps. First was finding C, and next is finding P, our equivalent rate of interest. And that's 1 plus I to the exponent C minus 1. So that's equal to 1 plus 0.005 to the exponent 12 minus 1. Okay. And that comes out to a value of 0.06168. Okay? If you were to convert that, that'd be about 6.17% interest. So the last item we need is N, and that's again equal to the number of years times the number of payment periods per year. Okay? Remember, we're looking for how many times we've made payments. So N is equal, we have, 10 years. And we have 1 payment period a year. So N is 10. So now we have calculated all our values. What you'll notice here is I've done 2 steps that weren't done in an ordinary simple annuity. The first item, C, okay, was that ratio. And the second item was P, which is finding that equivalent rate of interest, given that the compounding period frequency and how often you make payments, your payment period frequency, are different. So substituting these in, our future value is equal to our payments, $2,000, and that's times 1 plus 0.06168 to the exponent 10 minus 1 divided by 0.06168. Okay? So I'm going to calculate the brackets first, and if you do that, you get your future value is equal to 2,000 times 13.28 by 3. And if you calculate that out, you get $26,570.50. So notice, it's close, but not quite this answer. And again, some of that just comes down to rounding. All right? Let's look at another example. Canada Trucking set aside $1,250 at the end of each month for the purchase of machinery. How much money will be available after 5 years if interest is 6% per annum compounded semi-annually? So again, they're setting aside $1,250 at the end of each month, and interest is 6%, but it's compounded semi-annually, not monthly, which makes this an ordinary general annuity. So it's asking for how much money will be available after 5 years. That means we're looking for future value. So your future value in a general annuity is your payment times 1 plus that equivalent interest rate, P, to the exponent n minus 1 divided by P. So the same steps as we did last time. Your payment was provided in the question, $1,250. Your nominal interest rate, J, is 6%, which is 6 divided by 100, removing the percentage sign, which is 0.06. Your number of compounding periods, M, in this case is 2, because it's semi-annually. So your periodic interest rate, I, which is J divided by M, is 0.06 divided by 2, or 0.03. So now again, remember the 2 extra steps. The first is your ratio C, and that's the number of interest periods divided by the number of payment periods. So interest is semi-annually, which is 2, and your payment periods are monthly, which is 12. So 2 divided by 12 gives you a ratio of 0.1666. It's a repeating decimal. So your next item is P. Remember that equivalent interest rate. That's 1 plus your periodic interest rate to the exponent C minus 1. In this case, P is 1 plus 0.03 to the exponent 0.1665. repeating decimal, minus 1. So if you calculate that out, you get an answer of about 0.00494. Okay, and that's with some rounding. So your last item you need is your total number of payment periods, n. Okay, and that's equal to your number of years, 5, times the number of payment periods a year, right? And this is the end of each month, which means you have 12 payments a year. So in total, you're going to have 60 payments. So knowing all these values, we can now substitute them in. Our future value is equal to our payments, $1,250, times 1 plus, okay, remember this equivalent interest rate, 0.00494, to the exponent n, which is 60, minus 1, divided by 0.00494. So, if you calculate everything in the brackets out, okay, you get 69.64. So you end up with your future value is equal to 1250 times 69.641. And again, that's rounded. And what that gives you is a future value of $87,051.35. Again, slightly different than the answer that I've shown, but again, a lot of that comes down to each of these items being rounded. Okay? What you'll notice here is I followed the same steps that we've done in the past, again, with the exception of these two variables, the ratio C and this equivalent interest rate P, which allows you to do this calculation with the different compounding and payment period frequencies. So let's look at one more example. Find the future value of $2,500 deposited at the end of every 6 months for 10 years if interest is 6% per annum compounded quarterly. Okay, so I've noted that you're finding the future value here. So you start with the formula. Future value is equal to the payment times 1 plus your equivalent interest rate, P, to the exponent n minus 1, divided by that equivalent interest rate, P. So let's look again on the side at what we know. Our payment, okay, is given in the question, $2,500. Our nominal interest rate, J, is 6%, which is 6 divided by 100, removing the percentage sign, or 0.06. Our number of compounding periods per year, M, is quarterly, which means M is 4. So our periodic interest rate, I, which is J divided by M, is 0.06 divided by 4, which is 0.015. So now again, the two steps that we have to do that are additional. First is this ratio C, which is the number of interest periods divided by the number of payment periods per year. Okay, so interest periods is quarterly, which is 4, and payment periods is semi-annually, which is 2. So 4 divided by 2 gives you a value of C of 2. So now we can calculate our equivalent interest rate, P, and that's equal to 1 plus your periodic interest rate to the exponent C minus 1. And in this case, P is equal to 1 plus 0.015, and that's the exponent 2 minus 1. And if you calculate that out, you get 0.030225. All right? Last item, N, our total number of payment periods. So it's equal to 10 years. And we're paying semi-annually. So so that our number of payment periods per year is 2. So 10 times 2 gives you a total number of payment periods of 20. So if we substitute all these values in, our future value is equal to 2,500 times 1 plus 0.015, and that's the exponent 20. Oh, sorry, it's not that. See, it's easy to make this mistake. All right, I put in the periodic interest rate. Again, all of us are so used to doing the simple annuities, you actually, the difference is you have to substitute the equivalent interest rate. So it's 1 plus 0.030225, okay, not the periodic interest rate, the exponent 20 minus 1, divided by that same equivalent interest rate, 0.030225. Okay? So again, I'm going to calculate the brackets first. This is just for you when you're trying questions. So the future value is equal to 2,500. And if you multiply everything else in the brackets, you get 26.932. So if you calculate that out, 26.932 times 2,500, you get a value of $67,330. Again, with rounding, you'll see I'm off actually by 11 cents here. But that, again, just comes around. The answers aren't wrong, okay? But just something to keep in mind. And remember, you saw me do this in this video. I'm not editing that piece out of this video where I made the mistake of placing the periodic interest rate here. And it's a common mistake, okay? So that's something that I always look for when I'm looking through your tests, all right, to see if you made a mistake like that. Because it's a simple mistake that your process is correct. It's just one wrong number, all right? So the next item I want to look at is we found future value. Now I want to show you present value. And the method is exactly the same. Okay, so a few, I'm going to call them housekeeping items. For ordinary general annuities, remember, it's an ordinary annuity, so payments are at the end of each period. But the key item here is the compounding frequency and the payment periods are not the same. That's what makes it an ordinary general annuity. So just like before, all I'm going to do is take that variable P. Remember, P is 1 plus your periodic interest rate to the exponent C. Remember that ratio? Minus 1. So that's just going to get substituted for everywhere that I see I in the equation. So just like the future value formula, in the present value formula, all we've done is taken that periodic interest rate, I, and substituted in this equivalent interest rate, P. And all this is doing is trying to equalize it, it finds an interest rate that matches the interest rate that you would have applied with the number of payment periods that you're seeing here, okay? So I didn't go into how this formula was derived, but that's what it's doing, okay? Just like in the past, N is the same, it's the total number of periodic payments. Your payment, okay, is simply the amount you're providing during each payment period, or the amount you're getting if it's a loan. And PV is simply the present value. I've added the subscript G. Again, all that means is this is for an ordinary general annuity. And you'll see the difference rather clearly when you're using the formula with this value P. Okay? So let's go right away and look at an example. A loan is repaid by making payments of $2,000 at the end of every 6 months for 12 years. If interest on the loan is 8% compounded quarterly, how much was the original loan for? So a couple things to notice here. Payments are every 6 months, which is semi-annually, and your interest on your loan is quarterly. Okay, so those are different. They're not the same, and payments are at the end of the month. So that means it's an ordinary general annuity. So what we're looking for is what the original loan was for. In other words, the present value. So the present value is equal to your payment. And again, the formula is the same. 1 minus 1 over 1 plus. Instead of I, we replace P. Replace it with P, sorry, to the exponent N divided by P. So again, it's the same formula that you saw in the last unit with the exception of we've changed the interest rate P's I to become P. So what items do we know? Again, our payment, we know it in the question, $2,000. Our nominal interest rate is 8%, which is given in the question, which is 8 divided by 100, removing the percentage sign, or 0.08. M, our number of compounding periods, well, it's given that it's compounded quarterly. So M in this case is 4. So our periodic interest rate I is equal to J divided by M, or 0.08 divided by 4, which is 0.02. Now again, just like for future value, we have these additional 2 steps. The first one is the ratio C, which is your number of interest periods divided by your number of payment periods, both per year. Interest is quarterly, so it's 4. And your payment periods are every 6 months, which is semi-annually, meaning you have 2 payment periods a year. So your value for C is 2. So now we can calculate our equivalent rate of interest, P. So that's 1 plus our periodic interest rate to the exponent C minus 1. Or in this case, 1 plus 0.02 to the exponent 2 minus 1. And if we calculate that out, we get a value of P of 0.0404. So our last item we need is N, our total number of payment periods. And that's 12 years multiplied by 2 payments a year, which gives us 24. So substituting all of these values in, our present value is equal to our payment, which is $2,000, multiplied by 1 minus 1 divided by 1 plus 0.0404, our equivalent interest rate, to the exponent 24, divided by 0.0404. So again, I'm going to calculate the brackets first. And if I do that, we get our present value is equal to 2,000 times 15.1847. So if we do that, 15.1847 times 2,000, we get $30,369.40. So again, a couple of cents off from the answer listed here, but like I've said in the past, that's because of our rounding. So let's look at another example. A second mortgage requires payments of $370 at the end of each month for 15 years. If interest is 8% per annum compounded semi-annually, what was the amount borrowed? Okay, so again, we're asking for the amount borrowed. We're asking for the present value. And a couple things you'll note, payments are at the end of each month, and interest is semi-annually. Okay, so it's at the end of the month, but the compounding frequency is different. That makes it an ordinary general annuity. So we start with our formula. Our present value is equal to our payment times 1 minus 1 divided by 1 plus P, remember our equivalent interest rate, the exponent N, divided by P. So again, I start on the right-hand side. We know our payment in the question is $370. We know our nominal interest rate, J, is 8%, which is 8 divided by 100, removing the percentage sign, or 0.08. M, the number of compounding periods, well, it's compounded semi-annually, so M is 2. So we can calculate our periodic interest rate I, which is J divided by M, which is 0.08 divided by 2, or 0.04. Now again, the 2 steps we've added, being a general annuity, your ratio C, which is the number of interest periods divided by the number of payment periods. In this case, interest is semi-annually, which is 2, and payment periods are every month, which is 12. So that gives you 0.166 repeating decimal. So you'll start to see kind of patterns emerge for this ratio, because there's only so many different combinations you can have. Monthly and semi-annually, monthly and quarterly, quarterly and semi-annually. There's only so many ratios you can have. So you'll start to see that this number has common numbers, okay, depending on what the 2 compounding frequencies are. So finding your equivalent interest rate, P, remember that's 1 plus your periodic interest rate to the exponent c, that ratio we just found, minus 1. And in this case, that's 1 plus 0.04 to the exponent 0.166, it's a repeating decimal, minus 1. So if you calculate that out, you get a value of p of 0.006558. Okay? So our last item we need to calculate is n, okay, a total number of payment periods. So that's equal to 15 years, it's given in the question, and you're making payments every month. So 15 times 12, which gives you 180. So substituting all of these values in now, your present value is equal to your payments, 370, times 1 minus, and this becomes 1 minus, or 1 divided by 1 plus your equivalent interest rate, 0.006558, and that's all to the exponent 180, divided by 0.006558. Okay? So if you calculate everything out in brackets, you end up with the present value is equal to 370 times 105.4697. And if you calculate that out, you get an answer of $39,023.80. Okay? So let's look at one more example of present value, as to be the last example of this lesson. A contract will be fulfilled by making payments of $8,500 at the end of every year for 15 years. If interest is 7% per annum compounded quarterly, what is the present value of the contract? So, a couple things. You know it's a present value. You also know that payments are made at the end of every year for 15 years, and interest is compounded quarterly. So they're different, means this is an ordinary general annuity. Starting with the formula, the present value is equal to the payment times 1 minus 1 divided by 1 plus, remember that equivalent interest rate, p, to the exponent n divided by p. So what do we know? Okay, remember everything on the right-hand side. Your payments are $8,500. It's given in the question. Your nominal interest rate, J, is 7%, which is 7 divided by 100, removing the percentage sign, or 0.07. Your number of compounding periods per year, M, it's compounded quarterly, so M is 4. So your periodic interest rate, I, which is J divided by M, is 0.07 divided by 4, which is 0.0175. So now these two steps you have to add, remember. First is the ratio C, which is the number of interest payments divided by the number of payment periods. So your interest frequency is quarterly, and your payment frequency is the end of each year, which is annually, so 1. So your ratio C is 4. Now your equivalent interest rate, P, is 1 plus your periodic interest rate to that exponent C, that ratio, minus 1, or 1 plus 0.0175 to the exponent 4 minus 1. And that gives you a value for P of 0.07186. Okay? Your last item, N, total number of payment periods, is 15 years. It's given in the question. And you're making a payment at the end of every year, which is annually. So your value for N is 15. Substituting all these values in, your present value is equal to your payments, 8,500, times 1 minus 1 divided by, remember, 1 plus your equivalent interest rate, P, 0.07186, so the exponent 15, divided by 0.07186. So if you calculate the brackets out again first, your present value is equal to 8,500 times 9.002. So if you multiply that out, you get your present value is equal to $76,515.91. Sorry, I wrote that bad. Let me just, that's $76,515.91. Okay, so what you'll notice is the method of solving these didn't change. The only thing that did change, again, are these two equations. Okay, so that's it for this lesson. These are your practice problems for this section. If you have any questions, per usual, please send me an email or you can ask during our tutorial sessions. Thanks, everybody.